Welcome to the office. We're going to take a look today at a demonstration or a proof for the formula for calculating the surface area of a sphere. Excellent. To do this, what we're going to do is we're going to use a calculus-based approach, and we're going to use integration. Of course, right? It's calculus here. We're going to integrate to find the surface area of a surface of revolution. So if we think of a sphere as, see, make a horizontal axis here. If we think of a sphere as the rotation of the upper half of a circle, right, revolve that around the axis here, then we would end up with a sphere, and then we can calculate that surface area. Now, we want to integrate this, or we want to find a formula for this as easy as possible. And oftentimes with circles or spheres, it's easiest to consider polar coordinates. So we're going to consider essentially this to be the origin of the polar coordinate system. And we're going to use this idea for a surface of revolution. Now, what exactly does this look like? We're going to, again, using polar coordinates is going to look a little bit different than we would consider in rectangular coordinates, mostly because the formula just ends up being so much more simple. So what we're going to do is same thing as we did before in terms of calculating surface area. We're going to calculate the surface area of a strip. Okay, we calculate the surface area of this strip, and then we do that repeatedly to get the whole thing, right? We take this and we rotate it, is what we're doing. Again, looking a little bit different here, rather than considering where are we at and then considering delta x, right? That's not what we're doing in this case. We're going to use polar coordinates, so we're going to say, all right, here's some angle. We'll call that angle theta. And then what we're going to do is we're going to create our band, we're going to consider an increase in the angle. And this angle measure here would be d theta, right? The change in angle measure. And then we're actually going to go ahead and we're going to revolve this part here. So it's not a flat line or a vertical line, which is a little bit different than what we've done in the past. And that's okay. We can calculate the length of that surface, right? The length of an arc is simply the radius times the angle measure, radius times angle measure, which is d theta. And so in this case, that's actually the change in arc length, okay? So ds here. S is a lowercase s is a reference to arc length, and this is our change in arc length, so it'd be ds. We don't necessarily need that, but that should make some sense to us. All right, so we have the width of the strip. The width of the strip, of course, if we were to calculate the surface area, I suppose that doesn't need to be dashed. This one is solid. That one is dashed. There we go. If we were to consider this surface, right, the shell of a cylinder, the outside here, we have our radius, which is what we're interested in. Oh yeah, well, we'll get to that in a minute, I guess. So we have our radius, and then we have our width. So we would get the circumference of pi, 2 pi r times the width, and that would give us the surface area here. And we're going to do essentially that here. This height to give us our radius would be, think about this here, sine is opposite over hypotenuse. So if we go with the sine of theta times r, so r sine theta is going to give us our height here. That's our radius, so we can get an approximation here. So the circumference of the band or the strip here, this red thing, is equal to the whole circumference 2 pi r 2 pi times the radius. The radius of this thing is r sine theta. So that's going to give us, we're going to call it dA, the change in area for our sphere here. So dA would then be the area of the band or the area of the strip, which is circumference times the height. Or the width rather. So we're going to call it RD theta. So 2 pi r sine theta times r d theta. Excellent. So that's dA. And what we want to do then is if we want to find A, the surface area, all we have to do is integrate dA. Right? This is the integral of dA over the appropriate region. The integral of dA. Now, if I want to indicate a region, oftentimes that's denoted by a capital R. So rather than integration bounds, I don't know what I have to integrate over. If you don't like this notation, that's fine. All that I'm really saying is that I need to integrate. Well, our angle here can go from 0 all the way up to pi. And dA is 2 pi r sine theta r d theta. Of course, I could write that a little bit differently. This is the integral from 0 to pi. Actually, let me pull out those constants. So 2 is a constant, pi is a constant, and I'm integrating with respect to theta, not r. So r, I have an r squared out here, 0 to pi. And the only thing that's left is sine theta d theta. Now, I'm going to leave out the details here. At this point, it's just calculus 1. So this is going to give us, let's see here, 2 pi r squared times 2. So 4 pi r squared is the surface area of our sphere. Sweet. Okay, so that was a really quick presentation for the surface area or the formula for the surface area of a sphere. I would encourage you to check out any other resources or ask questions if you feel there are any gaps in this explanation. But thank you for your time and your attention. Have yourself a wonderful day.